So
Is the homework based on completion or is it?
So-
correction?
half the points are based on completion, and then I choose one problem in the homework to grade for correctness, and so that's gonna be worth half the points. Yeah.
My easy time.
You might be 100% whatever again. Are you just clicking through slides?
Me? No, the teacher's just kind of reading off the notes.
Obviously.
Yeah, but yeah, so it's I'm kind of bored the entire time.
It's better than looking at the slides and being like, what are you looking at?
It's a boring ass class to go on, so I really hate it. It's not like I
Really?
yeah.
At least he writes them.
Yeah, exactly. That's like the only saving grace that he writes. But then when he explains stuff, I think. But that's like the derivations. It's like nobody cares, man. Everybody just cares about the final answer. Nobody cares about the derivation. Yeah, poor guy. It's more than slave doing.
You start them more people.
We got really. We got. That integration. And we got the class that didn't like.
Right, thanks so much. My number got out this scammer. I'm trying to scam. US.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, staying dry, hopefully. A lot of rain today. I was half expecting to get a text at 10 o'clock this morning after getting here that said campus is closed, but thankfully that didn't happen. So we're all here. Okay, so the plan for today, we're gonna start a new topic today called rate of return analysis. So we have a whole new set of notes on that. I will say that the content for the first midterm. So remember, the midterm schedule this semester is kind of pushed back a little bit, just because of the kind of anticipated strike in week 1. So we're actually all done with the midterm 1 content, and so midterm 1, kind of the cutoff for that was annual cash flow analysis. So we finished that last week. So I do have one more homework for you guys to do. It's going to be just based on present worth analysis and annual cash flow. So I'm going to post that today. I know homework 2 is due tonight or tomorrow night, but you guys can go ahead and get started on homework 3. And then we'll have the midterm exam, I think not next week, but I think the week after. Okay. Okay, so today, yeah, rate of return analysis, new topic. This is rate of return is not going to be on the first midterm, but it will be on the second midterm that we're going to take, closer to spring break. Okay. All right. Any questions I can answer before we get started for today? Okay. All right, so let's go and get started. So topic for today is rate of return analysis. Okay. So, for the past couple of weeks, we've been going over, kind of these basic economic analysis techniques. So we've gone over present worth analysis. We spent quite a bit of time on that. Last week we did annual cash flow analysis, and we saw that it was similar. Rate of return analysis is in that same category, so I would still categorize it as kind of like a basic economic analysis technique. Although the way we do rate of return is a little bit different. But let's start by saying that the rate of return supposed to be I don't know why I wrote it like an A. So these 3 kind of form the trio. And in fact, after rate of return analysis, we're going to shift gears a little bit in this class and talk about things like taxes and inflation, stuff like that. But for this first, this first half of the economic section, we're just going over analysis techniques, right? So that's what all of these are. Rate of return is a bit different though. The biggest difference in rate of return is that, for all the problems that we've gone over at this point, the interest rate has been something that's been given to you, right? And so I said, here's a situation, here's the interest rate, give me, the present worth analysis, right? Rate of return actually kind of flips that a little bit, where in rate of return analysis, I'm going to give you all the cash flows for the problem. And what you have to do then is you have to compute the interest rate. Okay? In fact, that interest rate that you compute is literally that's what's defined as the rate of return. Okay. So rate of return is a term that's kind of thrown around in economic circles quite a bit, but for the most part, people refer to it as an interest rate, or at least kind of the way that we use it as an interest rate. Okay. Of course, the way the rate of return got its name is that it's the rate at which an investment returns money to you. Okay. And that rate is usually given as a percentage of your original investment. So that's kind of how it got its name. But in more broad sense, you can also apply this analysis to loans. You can apply it to kind of more complex engineering or budget situations. And then the interest rate you compute is the rate of return. Okay. So even though the name rate of return here implies some kind of investment, we apply it in a much more broad sense to just compute interest rates. Okay. And so I think the best way to illustrate this in action is to just do an example. So let's do a very simple example first, just to kind of give you an idea of kind of how we're going to do this. Okay. Okay. So let's say that you are lending out money to someone. And let's say that you've lent out $5,000 to your friend. Okay. Your friend has agreed to pay this money back with interest, of course. And what they've agreed to do is that they've agreed to give you 5 equal payments of $1,252. Okay. All right, so what we want to compute here is we want to compute the rate of return of this. In your case, it's an investment. Okay. All right. So the amount of money that you are going to get back from your investment is obviously greater, even if you just take the raw money amounts, right? You take 5 times 1252, that's a bit over, that's a shy over $6,000. And so, you're going to be getting a return on your investment. And so you want to compute the interest rate from that. Okay. Of course, it's not as simple as just taking the raw money amounts and dividing it by your initial investment. Remember, the value of money is going to change over time. Okay. And so that's all going to affect our analysis here. Okay. I guess I should also point out that I guess it doesn't really matter for this problem, but these are monthly payments. So it's a little bit of the wording. So the interest rate that you're going to compute here is a monthly interest rate. Okay. All right. So let's start by illustrating this. So let's draw our cash flow diagram. I drew 6 just because I drew the line too long, but we're not going to go up to 6. Okay. Okay. So from your perspective in this analysis here, you're lending out $5,000. Okay. So that is basically the same thing as a present day or initial payment of $5,000. Okay. And then each period after that, you're going to be getting a uniform series benefit of 1252 5 times. All right. So basically what we have here is we have a present day sum of $5,000. And what we're saying is that this is equivalent to a uniform series of 1252. Okay. Okay. So we can, so based on that statement alone right there, we can set up our equation, okay? Of course, we don't know what the interest rate is here. We're going to be computing that, okay? And so what we're saying here is that a present day sum of 5,000. Okay, this is going to be equal to a uniform series of 1252, okay? But in order to have this equal sign here, we have to do our conversion, right? And so, in this case, the conversion that I'm going to use here is one of a present worth conversion. And so I'm going to take that 1252 and convert it to a present day amount, okay? And so we have a P over A. We don't know the interest rate, so we're just going to leave it as a generic I. And it's going to take place over 5 periods, okay? All right, so remember, in order to state equivalence, we have to convert all the cash flows into the same form. So converting 1252 to P. All right, so there's a reason why I saved rate of return from last, because the intuition and the and kind of the techniques that we've picked up in present worth analysis and annual cash flow analysis, those same principles kind of apply here as well. Okay. So of course, we can't complete this equation because we don't know what I is. Okay. But we can solve for it. And so let's isolate that conversion factor. Okay. So the way I'm going to do that is I'm going to divide both sides by 1252. Okay. Just to kind of get the conversion factor on one side of the equal sign by itself. Okay. And so what we get from that is that we get P over A, I, 5. This is equal to 5,000 divided by 1252. We just do some quick math there, punch into a calculator. We get 3.994. Okay. All right. So we don't know the interest rate, but we do know what the conversion factor is. Okay. And so from here, one way that you can solve for the interest rate is to use the compound interest tables. So we can search through. We're going to search through the compound interest tables for the n is equal to 5 row. Okay. And of course, the column that we're going to be looking at is the P over A column. So we know exactly where in the tables that we're going to be looking for. We just don't know which table to find. Okay. And so you're going to scroll through the compound interest tables, and unfortunately, there's really no kind of convenient way to do this. And so you're going to be kind of scrolling through a lot of pages, looking for the n is equal to 5 row and the P is over A column. Okay, and you're going to find the entry that's equal to 3.994. Okay. And I think I still have the compound interest tables here on this computer actually. So let me go ahead and once everyone's done writing this down, I'll go ahead and switch here so I can just kind of show you how to do this. Okay. So it's a little bit inconvenient. It's not the it's a little tedious, but it's also kind of straightforward, but so you'll see. Okay, so let me go ahead and switch over here. I believe I should have the compound interest tables here. Yep. Okay, so here we have your compound interest tables. Let me scroll up a little bit just so you can. We'll start with interest rate 4%. Okay. There's no reason to start at 4%. I just don't want to scroll that much. But in reality, you know, you'd probably start, you know, somewhere closer or maybe somewhere up as well. Okay. It's a lot of guess and check. You'll see when we kind of do a more involved example a bit later. Okay. So we know that we're on the compound interest tables for 4%. Okay. And so remember, we're going to look at the n is equal to 5 row. Okay, so that's the 5th row in the table. And we're going to look at the P over A column. Okay, bless you. And so if we look at that entry here for I is equal to 4%, we see that our conversion factor is 4.452. So this is not it. Okay. So let's go to the next table. So let's go to 4.5%. Okay. So now we're on the table for 4.5%. We're going to look at the n is equal to 5 row, the P over A column, and we get 4.39. Okay. So you can see we're getting warmer compared to the previous one, but we're not quite there yet. And so let's scroll down. I'm going to skip ahead a little bit. Okay. Let's look at interest rate 6%. And so we'll look at the n is equal to 5 row, P over A column. We can see our conversion factor here is 4.212. So again, you know, getting warmer, but not quite there yet. Okay. We look at the same entry for interest rate of 7%. We can see this is 4.1, right? Almost there. And then we come into 8%. And so at 8%, we get, we look at the n is equal to 5 row, P over A column. You see that we have a conversion factor here of 3.993. So, you know, the one that we computed in the problem is 3.994. Not 100% exact, but it's within, you know, it's within less than 1%. So, you know, this is pretty good here. And so based on this, we can see that, you know, the rate of return or the interest rate for this problem is going to be 8%. Okay. All right. Any questions on this example here? Yeah.
Is there any other way to find it, or do you have to use the conversion tables?
So there is another way, but the other way involves using the formulas where it's a little bit hard to solve those algebraically. You'll see just because the powers are really high in that one. But you can use plotting. So if you're kind of savvy with MATLAB or Excel, and you can plot the formula, you can find where it crosses the x-axis, and that's going to be your rate of return. So yeah, that's the next example we're going to do. Okay. Okay, so let me come back to here. All right. And so based on what we found from the tables, we get I is equal to %. Okay. But of course, you know, that's you know, depending on how you feel about scrolling, let me maximize this. It's not the most convenient way. In fact, you know, even for me too, I find it a little bit kind of annoying and tedious to search for the tables. But you can set up a formula to solve for the same thing. And so you would set it up basically the same way. And so let's start with our same equation here. Okay, so we have 5,000 is equal to 1252 P over A, I, and 5. Okay. Except instead of looking this up in the table, let's use our formula for P over A. Remember, we had all these formulas for converting between the different cash flow types that we went over at the beginning of class. Okay. All right. So our formula here for P over A, I'm just going to write the generic one first, is 1 plus I raised to the n minus 1, all divided by I, 1 plus I to the n. Okay. Of course, you know, we know what n is. We know n is equal to 5. And so let's go ahead and plug that in. So we have 5,000 is equal to 1252 times 1 plus I raised to the 5th power minus 1 divided by I, 1 plus I raised to the fifth. Okay. All right, and so technically speaking, we have an algebraic formula here. It only has one unknown, and technically you can solve this equation for I. It's just that algebraically, because of the fifth power here, it gets a little bit nasty to do. Especially, when we do more complicated problems and you have, especially non-standard cash flow conversions, solving for I outright from these formulas is, challenging to say the least. Okay? And so the way that I actually recommend solving this is to using a plotting software. So you can either use graphing calculator, you can use MATLAB, or you can use Excel. So let's plot this. And of course, to plot it, you have to put everything on one side of the equal sign. And so I'm going to go ahead and move the 5,000 over to the other side. Okay. And so if we move 5,000 over to this side, we get 1252 times 1 plus I to the fifth power minus 1 divided by I times 1 plus I to the fifth power minus 5,000. Okay. And so now you can either plot this in your calculator where I here is your independent variable, okay? Or you can plot it in MATLAB. Usually MATLAB is kind of my go-to. So it's honestly just 4 lines of code. So let me show you kind of how I did it. So in MATLAB. By the way, MATLAB is not required. It's not a prerequisite for this course, but usually once you kind of take 401, you've probably taken 205 already. And so I'm showing this to you, not as something that you're required to do, but it's if you're savvy in MATLAB and if you like using MATLAB, this is how you would do it. But you can solve these problems without MATLAB as we've kind of just seen. Okay, so the way I solve it in MATLAB, I create a variable. I'll call it X. So X here is going to be it's going to represent I. So let's create a vector with this. So let's start it at 0.06, colon, 0.001, 0.1, okay, semicolon. So what this line of code here does is that it creates a vector for plotting interest rates, in this case, between 6% and 10%. So that's going to form our horizontal axis. That's our x-axis for the plotting. Okay. Now we need to create a variable for the y-axis. Okay. And so for the y-axis, we're going to plug in our formula that we have up here. And so we're going to say present worth. Okay. This is going to be a new variable. Present worth is equal to 1252 times. And we're going to have a lot of parentheses here. So 1252 times 3 parentheses here, 1 plus X dot caret 5 minus 1, close parentheses, okay. Dot divide X dot star 1 plus X dot caret 5, 2 close parentheses, semicolon. Okay. Oh, got the minus 5,000. Okay. So this here creates y-axis. Okay. Creates our y-axis for plotting based on the formula that we had above. Okay. So now we have our X values, we have our Y values. So now all that's left is to plot it. Okay. Okay, so I'm going to create a figure. I think that's all. If you're just creating one figure, you don't have to put figure one, but I just do it out of habit. Okay. And then we're going to plot X and present worth. Okay. And so what this does is that it creates our plot. And so if you run this code, this simple 4 lines of code here, you're going to make a plot. Where the horizontal axis is X, the vertical axis is our present worth. Okay. And then if you do that, it's going to create a plot that kind of looks like the following. Okay. It's approximately like, okay. Where at some point, this this graph is going to cross over the horizontal axis. Okay. And where the plot crosses over, this is your rate of return. And for this problem, since it's a repeat, it should cross over at 0.08 approximately. All right. So that would be the other way to solve these problems is by plot. Okay. So you either have the table approach or the plotting approach. So for your homework problems, it doesn't matter to me which method you use. But I will say that for the exam, not for the first midterm, but for the second midterm where this is going to show up, it's going to be a closed computer exam, so you're not going to be able to plot things. And so even if you prefer to use the plotting method, just for practicality's sake, I would at least be familiar with the table method, just so that you can do it for the exam. Okay. All right, questions. My plot showed up as a vertical line and Desmos with x-intercept at 0.08. It probably depends on how you set your bounds for for the horizontal and vertical axis. Yeah. But if the x-intercept is at it's 0.8. Oh, 0.08. Yeah. That's probably because of the bounds that you may have set. Yeah. But if the x-intercept is at the same place, then that you probably set up correctly. All right, any questions on that? Okay. All right, and so that's the basics of rate of return. So we've done kind of a pretty simple example here. Of course, it does get more complicated than this. In reality, you have a lot more different cash flows. So let's kind of take a step back and talk about kind of a general methodology for actually computing rate of return. Okay. So no matter which way that you use, no matter if you use the table method or you use the plotting method, in order to get to that point, before you actually either use the tables or you use, plotting software, there's a little bit of setup that you had to do. Okay, we kind of glossed over a little bit on the past example just because it was so simple. But honestly, most of the work that you're going to do in rate of return is actually in this setup here. So to compute rate of return, you always have to set up an equivalent equivalency equation. And it is that equivalency equation that we're going to use to solve for I. And so there's a couple of different ways you can set up this equivalency equation. They're all essentially the same thing. It just kind of depends on how you interpret it. Okay. So the one that we did previously, in the previous example, was we computed the present worth of all the costs. Okay. And then we set that equal to the present worth of all the benefits. Okay. That's usually a pretty straightforward one to do, just because, when you're analyzing an economic situation, all the costs usually kind of jump out at you, all the benefits jump out at you. You just put all of those on one side of the equation, all the benefits on the other side. You convert everything to present worth, and then there's your formula for that. Okay. So I think, that's probably the most common one. That's the one that I personally use, the most. There's different spins on this. And so another way that you can formulate this is you can say the net present worth. So that includes all the costs and all the benefits with their appropriate sign, of course. And so costs being negative and benefits being positive. The net present worth is going to be equal to 0. Okay. And in fact, you can get the net present worth is equal to 0 from the previous one. You just subtract, present worth of the cost from both sides. And so, okay. But, it's just another way to interpret it. You can approach this from an annual cash flow perspective as well. So you can say that the EUA C, so that's the equivalent uniform annual cost. And so that's all the costs converted to a uniform series. That has to be equal to EUAB, which is the equivalent uniform annual benefit. So all the benefits converted to a uniform series. Okay. So equation 3 is the exact same as equation 1, it's just that everything is a uniform series instead of a present worth. Okay. And then by that same token, you can just subtract the EUAC from both sides, and you can say that the equivalent uniform annual worth, okay, which combines both of the benefits and the costs, has to equal to 0. Okay. So all of these work. So this is kind of the setup that you have to do kind of before you either choose to do the formulas or the table and whatnot. Okay. So again, this is one thing where it's kind of just a personal preference thing, and so just whatever kind of makes the most sense to you. The only thing you just have to make sure is that you just have to make sure you be consistent. Right? So one thing you can't do is that you can't do a present worth of the cost and set that equal to the EUAB, because that's two different types of cash flow. So I would say just pick a cash flow type and then stick with it, convert everything to that cash flow type, and set up your equation. So this list here makes it seem like you have a lot of options, but they're all kind of essentially the same. So you just convert all the cash flows to the same type, set up your equation, and then just have at it, either with tables or with the formulas. Okay. All right, any questions on this before we jump into another example? Okay, all right, so let's do another example. All right. So let's look at this cash flow diagram. And what we want to do is, considering all of the cash flows here, we're going to compute the rate of return. Okay. So our cash flow diagram looks like the following. So we have 0. I made the line too long. That's fine. 0, 1, 2, 3, 4, 5, 6, 7. Okay. So for the first 4 years, including year 0, we have a benefit of $9,000 per year. I'm going to use colors here to save myself on a little bit of writing. So everything in green there is 9,000. Okay. And then in years 5, 6, 7, 8, 9, we have an equivalent cost, okay? Or uniform cost, excuse me. So all of these here are in the amount of 8,316. Okay, so we want to compute the rate of return here. And so you can see this situation here is a bit more complicated than our first example. We have some non-standard cash flows here, but we're going to take the same approach. And so we're going to use one of the 4 approaches that we have up here. And then in this problem, I'll show you how to use the tables to solve this one, just because it gets a little bit complicated. Okay. But that's our situation. Any questions on the setup for the problem? All right, so let's set up our equivalency equation, and I'm going to use present worth. Okay. So I'm going to take all these cash flows here and convert it to a present sum. Okay, let's start with the benefits. You have to be careful with the benefits a little bit here, because it looks like we just have one uniform series, but we actually have 2 different types of cash flow, because you can see that our uniform series here actually starts on year 0, which is kind of non-traditional, right? Remember, the standard form for uniform series actually starts on time period 1. Okay, so the fact that we have something that starts on 0 here is quite unusual. Okay. So we're going to break this up, actually. So we're going to break this up into one present sum of $9,000. Okay. And then we also have a uniform series of 9,000 from years 1 through 3. Okay. All right. And so if we compute the present worth of the benefits, that $9,000 in year 0, that is already a present sum, so we don't have to do any conversion there. Okay. But that is $9,000 plus 9,000. Okay. We have a uniform series for 3 years, and so we have P over A. We don't know the interest rate. That's what we're solving for. So we have P over A, I, and 3. Okay. Okay. So that is the present worth equation for the benefits. Now let's do the same thing for the costs. So you can see here we have a uniform series of 8,316. Okay. But, this does not start until year 5. And so if we're going to bring this back into the present day, into P, we have to do a non-standard conversion. Okay. Okay. We have present worth of the costs. We have 8,316. So this is pretty similar to an example that we did before with non-standard conversion. So remember, there's more than one way to do this. But this is typically what I like to do. So first thing I'll do is I'll convert it into a single sum. Okay. Okay. So that's going to be P over A. And we're going to count how many times this repeats. And so this repeats 1, 2, 3, 4, 5 times. Okay. And so by doing this conversion here, we're going to convert all this into a single sum into the time period right before the series starts. Okay. And so this series starts on year 5. And so if we convert it all to a single sum, that's going to put it on year 4. All right, and so from that single sum in year 4, we're going to move that back in the past to year 0. And so that's going to be a P over F conversion, I, and a 4. So that converts our single sum in year 4 back to year 0. Okay. So we needed to do a non-standard conversion here because we had a uniform series that did not start on year 1. This started on year 5. Okay. All right. Any questions on how we set that up? Okay. All right. So now that we have the present worth of the benefits, we have the present worth of the costs, we can set up our equation. We're going to have the present worth of the benefits equal to present worth of the costs. Okay. We'll just plug in the expressions that we have above here. So we have 9,000 plus 9,000 P over A I3 is equal to 8,316 P over A I5 and then P over F I3. Of course, we don't know what those conversion factors are, and so we can't actually plug in for them. But we can make this equation a little bit easier to begin with. So let's move everything over to one side of the equation so that we have 0 on this. And so I'm gonna move the cost. I'm gonna move that over to the left. It kind of helps just for intuition too, so that benefits are positive and costs are negatives. Let me box this for a second, just for emphasis, we're not done yet, okay, so we haven't solved for I just yet. But this is kind of a good spot to kind of pause and kind of, I take a step back, okay? All right, any questions on how we got to this point here? Okay. All right. So now we have this equation here, right? And so in theory, this is an equation that we can use to solve for I. If you're going with the formula approach, what you would do from here is you would plug in the formulas for all your P over A, your P over F, okay? This one you're definitely not solving by hand, so you're definitely solving this one by plotting. And so you would plot it in your calculator, you plot it in your computer, MATLAB, Excel, whatever program you use, and then you just find where it crosses the x-axis, okay? So if you're solving this by plotting, we're basically done here, minus just some tedious coding you have to do, okay? But let's say that, we don't have access to a computer, right? We don't have access to a graphing calculator. So how would you actually solve this one? If you look at this equation here, compared to our first example, it's quite a bit more complex, okay? And the one thing that should jump out at you is that, we can't isolate a conversion factor on its own. In fact, we have several different conversion factors with several different versions or numbers of n, okay? We cannot. Okay. So we can't isolate a conversion factor on its own here, like we did in the first example, okay? And so the way that we're going to solve this using tables is not going to be as simple as just kind of solving for a conversion factor and looking for that value in the table, right? It's going to be a bit more complex. Okay. But one thing that we do know is that every conversion factor here uses the same interest rate because they're all part of the same problem. And so what that means is that we can take advantage of that. And so, it's still going to be tedious. And so this is still going to involve, going to different tables and kind of plugging in, but we can kind of take like a guess and check or plug and chug kind of approach until we satisfy this equation. Okay. And so you're just going to keep doing that until your equation here is satisfied. Okay. And by satisfied, I mean, you get something that equals 0, or at least close to equal 0 here. Okay. All right. And so there's really no elegant other way to go about this than just start chugging. Okay. So let's start chugging in. And so, I'm going to start from the very beginning here, but in reality, usually, for these types of problems, you have some kind of idea of where to start looking. And so you don't have to start looking from 1% like here from scratch. For the homework problems, it's a little bit of a I guess maybe not as satisfying experience as on the homeworks, like I give you the solution for homework. So you'll know right away just by looking at my posted solution where to look. But in reality, sometimes you have to search a lot. Okay. Okay, so let me tell you what I mean here. So let's start with I is equal to 1%. Okay. And so we're going to go to the compound interest table for the 1 for 1%, and we're going to plug in for each of these conversion factors. So for all 3 of these. Okay. Okay, so for I is equal to 1%, we plug it in, and what we get is 9,000 plus 9,000. For I is equal to 1%, that P over A I3 is 2.941. Okay. Minus 8,316. And then we plug in these conversion factors. For this one, P over A, I, and 5, this is 4.853. And then the P over F, I3, this is 0.961. Okay. All right, so we punch those into a calculator, and what we get is minus 3,314 and 60 cents. Okay. So not quite, right? So we're trying to get zero here. So the fact that, we're at minus 3,000 means that, we probably still have a ways to go. Okay. So let's try 2%. All right, so if we try 2%, we're going to write the same formula here, except the only thing that's going to change here are conversion factors. Okay. And so for I is equal to 2%, our P over A I3 conversion factor is 2.884. And then our other conversion factors here are 4.713 and then 0.9238. Okay. We plug those in, we compute this, we get minus 1250.78. Okay. So we're getting warmer. Okay, so we're at least going in the right direction here. So, we started at something really negative. We ended up something that's still pretty negative, but less negative than before. So, we're at least knowing we're getting in the right direction. All right, so let's try 3%. Okay. So we scroll down the compound interest tables, we go to the one for 3%. We get 9,000 plus 9,000. 2.829 minus 8316. That first conversion factor is 4.58. Second one is 0.8885. All right. And so we plug all those in, we get a positive 6,020 and 45 cents. Okay. So we're very close, right? And so, you can see that in between 2% and 3%, the sign changed. And so we went from a negative present worth to a positive present. Okay. And it doesn't matter if you go negative to positive, positive to negative. You're basically just looking for a sign change. Okay. Because what that tells you is that, if you look at the plot that we made earlier today, right? The present worth line it's not one that wobbles, right? It's not one that looks like a sine wave. Usually you're only going to cross the x-axis in one location. Okay. And so the fact that we went from negative to positive here, that means that the rate of return is somewhere in between 2 and 3%. If we had to hazard a guess, probably it's a little bit closer to 3% because 620 is a little bit closer to 0 than minus 12. Okay, so it's somewhere in between there. All right. But of course, having it be somewhere in between is not exactly a satisfying answer. We want to find out exactly what the rate of return is. But we do know where it's between, okay? And so in these situations where, you know, the true answer is kind of in between two extremes, what we can do is we can interpolate. You guys are familiar with interpolating, I'm guessing, probably, I think probably used in thermodynamics, probably some other classes too, okay? Okay, and so if you have a good sense of how to interpolate, you can just kind of rely on that. I have a formula here if you want to use that, if you prefer to use that one as well. Okay. So our rate of return, so IRR, okay, so the IRR stands for interpolated rate of return. Okay. All right, question. So doesn't interpolation only work accurately with linear lines? That's a great observation. So yes, so interpolation, you're inherently making the assumption that you have a linear variation between the two extremes, right? In this case, you know, you can definitely make the argument that we definitely don't have a linear relationship because we have, you know, exponents of, you know, 3, 4, 5, 6. But the thing is, you know, with and this applies for most curves that, you know, if you're comparing between 2 points that are close enough, you know, 2 points that are close enough almost always have a line that's linear in between them. And so it's definitely an approximation for sure what we're doing here by interpolating. But if you're going to use 2 points that are close, like 2% and 3%, you know, it's usually a reasonable assumption that we can make that it's approximately linear in that regime. Yeah. It's a little bit different than, you know, let's say that you interpolate between 1% and I don't know, 8%, right? Okay. And so if you interpolate between 1% and 8%, you know, the true rate of return is indeed somewhere in between there. But because the range is so big, then that's when your approximation error really hits you. And so if you're going to use interpolation, it's almost always within kind of a small band. And so even if you don't have even if the formula underneath it is not linear, it's usually close enough to linear that you can say that it's a reasonable assumption. Yeah, you bring up a good point though, because what I've seen in the past for rate of return is that people, you know, just they say that, oh, the rate of return is somewhere between, you know, 3% and 15%, and they interpolate in between those and they say, you know, you're going to get in the ballpark, but it's not quite right. And so it'd probably be better to do between 7 and 8% because that's a small band. Yeah. Mm-hmm. Okay. So the formula that I have for interpolation is here. Okay, so you have the low interest rate, so that's I low plus the difference between I high minus I low. Okay. And you're going to multiply this by the quantity 0 minus present worth low divided by present worth high minus present worth low. Okay. Okay, so just a bit of clarification here because this formula can be a little bit confusing to use. Okay. So I low, okay. I low refers to the lower interest rate between the two that you're interpolating between. Okay. Because whenever you're interpolating, there's a high one and a low one. Okay, so I low and I high, pretty self-explanatory. Okay. But where it gets complicated is, or where it gets a little bit tricky sometimes, is when you're plugging in for PW low and PW high. Okay. So PW low, you would think that refers to just whichever present worth is lower, but this actually refers to the present worth correlated with the low interest rate. It's not actually the lower present worth. Okay. And by the same token, I high is the higher interest rate. And PW high is its corresponding present. Okay. So for this particular example, you know, the two are correlated. So the present worth for I is equal to 2% is actually lower than the other one. Okay. But if you had a situation like this, so let's say that we were checking I is equal to 2%, and then we get present worth is equal to, I don't know, 500. Okay. And then I is equal to 3%. Present worth is equal to minus 250. Okay. Just a thought example. Okay. All right. So in this case, I low is equal to 2%. Okay, because that's the lower interest rate. PW low here is going to be 500 because that's the present worth that's associated with that 2%. And then I high here is 3%, and PW high is going to be minus 250. Okay, because that's the present worth associated with that 3%. Okay. All right. So just a word of caution, because I think you know, people get confused sometimes using this formula. Okay. All right. Any questions on this so far before we finish up this example? Okay, so let's use this formula here. And let's finish this out. Okay. So let me scroll back up here. Okay. So since our present worth here changed signs, we can say that this minus 1250.78, this is our present worth low. Okay. And this positive 620 here, this is present worth high. Okay. And then I low is 2%, I high is 3%. Okay. All right, so let's go ahead and plug all those in. So this is kind of just a side example here. Okay. So you have IRR is equal to 0.02 plus 0.03 minus 0.02 multiplied by 0 minus 1250.78 divided by 620.45 minus negative 1250.7. All right, so from here, it's just the arithmetic. Okay, so you can just plug this into your calculator, and what you get is IRR is equal to 0.0267. And so if you convert this to a percentage, that's typically how it's reported. So you just multiply by 100. And so our rate of return in this problem is 2.67%. Right. Any questions on how we finish that up? All right, so that's rate of return analysis in a nutshell. And so, we went over a couple of different methods today. Just for the sake of consistency, and that's probably right up my homework solutions too. I'm gonna favor towards the table method, which is kind of what we just did. But of course, on the homeworks, if you feel more comfortable, or if you want to practice MATLAB or whatever, you can definitely plot all these and use the formulas, and you're gonna arrive at the same answer. Okay. But just remember that, when I do ask you to do this on an exam, I'm not, it's going to be closed, closed book, closed computer, everything. So I would definitely at least learn the table method just so that you're prepared for the exam. Okay. So one last thing before we head out for today, I want to just give you a sneak preview of what we're going to do on Thursday. And so what follows this brief intro is another example. It's quite a lengthy example, so I don't really want to start it today, but we will get into it on Thursday. Okay. But the next section here is going to be how do we actually apply rate of return to our to our analysis technique. Okay? Because being able to find the interest rate is useful. In fact, this is if you are into investing, or if you're kind of in that space, you own your own business, this is definitely a good skill to have. Okay. But remember, when I started today, I told you that rate of return kind of belongs to the same family as present worth analysis and annual cash flow. Okay. And remember, the primary way that we use present worth and annual cash flow was to perform comparisons. Okay. And so you can use rate of return to do comparisons as well. Okay. And so for situations where you need to choose, one economic option over the other one, okay? And so you would think that what you would do here is that you would just simply compute the rate of return of one option and compute the rate of return of another option, okay? Okay. And so what you would think you would do is that you would just compute the individual rates of return, find the one that gives you the greater rate of return, and then just choose that one, okay? But of course, the reason I'm saying it like this and the reason I'm presenting like this, that's actually not how you do it. Okay? Because in doing so, you're neglecting something that's actually very important, which is an opportunity cost. And what I mean by that is that, usually when you're comparing options in reality, they often have very different financial costs, right? So one is going to be more than the other one. Okay? Usually when you're on an engineering project and you're managing the budget, you have a certain amount of money that you can use to purchase assets, to purchase resources. Okay. If you go with the cheaper option, whatever that may be, what that means that you're going to have budget left over. Okay. And that budget left over is not going to be used for anything. Okay. Of course, you can always reinvest that money and do other stuff, but this opportunity cost is something that's important to consider. Okay. And so to deal with this, rate of return analysis actually handles it very well. And so you can modify rate of return to perform something called incremental rate of return. where to compute incremental rate of return, you're going to combine, you know, and I'm going to use present worth, just so but you can definitely do this with annual cash flow as well. You're going to take the difference between the net present worth of both options and then compute the rate of return on that. And so that's going to give you a better idea of, you know, if you go with one option, you're kind of giving up some things with the other one. Okay. So I'll give you one very, very quick example here. Okay. We're actually going to analyze this one in depth next time, but I'll kind of show it to you just to kind of start building some intuition here. Okay. So let's say that you're given a choice between two options, and this is just for your own personal investment. So let's say that you have the option to either invest $100 and earn 50. So you invest $100, you get that $100 back, and you get $50 on top of that. Okay. So you can just do the math real quick. This is a 50% rate of return. Okay. Well, option B, you can invest $200 and earn 80. Okay. Okay. So if you go with option B, you would invest $200, you get that $200 back, and you get 80 on top of that. Okay. And so if you just compute the raw rate of return here, this would only be a 40% rate of return. Okay. And so based on that math, you would say that option A is better, right? So option A gives you more bang for your buck. Okay. That's true. Okay. But what this problem doesn't tell you is that you can't do option A twice, right? And so let's say that you have $200 that you want to invest, right? You can either do option A, where you take your $100 and get back 50. Okay. If you go with option A, then you have $100 of your money that's essentially doing nothing. Right? And so it's almost like a waste. And so with option B, even though you have a lower rate of return, you can at least utilize all of your budget here, all of your $200, and you earn more overall money. Okay. And so this is something that you're going to miss if you just use traditional rate of return. But what we're going to learn on Thursday is incremental rate of return, which actually takes this into account, and will actually tell you kind of the better option to choose, which is B in this case. Okay. All right. Any questions on this before we wrap it up for today? Okay. All right. So that's all we got time for today. And so I will see you guys back here on Thursday. We'll start with an example right off the bat on Thursday, kind of illustrating this. And yeah, so hope you guys have a good rest of your day. Stay dry. You know, if you're driving out there today, be careful. There was a big accident today when coming to work. So, you know, definitely want to be careful driving. So, stay safe out there, guys, and I will see you guys on Thursday. Thanks, Braden. Where did you go for your office? So my office is in engineering building, E220. You could just stalk me back to my office.
That's
You guys,